So I changed the title of my talk. It actually would fit much better to what Hans-Christoph was telling us about, because I'm going to talk about an impurity in a multi-component gas. Okay? So if you want to talk about solitons, please come and chat with me afterwards. Okay, so the idea is that effectively this event is already the first milestone of us having a consortium that involves Gediminas that already delivered the milestone before us ever receiving the money, and now accidentally received the money, so now we are here celebrating with you. So this is a funny thing, and we called it Quasimodo because we thought that we would like to collaborate together on multi-component let's even write it. That was what we agreed, the 7 of us, of what we would like to work together. And then asking an LLM what would be cool acronyms, we came up with Quasimodo. So this is just that you're a bit in the notion of how it got to be here today. And because of that, I also changed my title. So I hope that it will be entertaining nonetheless. So generally in my research group, or my research interests involve taking many body degrees of freedom, bringing them together, and then if we want to go multi-component, we would think about the fact that it would interact with so many other things that then would give us finite lifetimes to the experiments, for example, or we could harness these additional degrees of freedom into the system and see whether we get something new that comes out if they come and interact. And then, of course, in quantum engineering, there's additional knobs. You could cycle. You could get new types of box distributions, for example, and get new types of physics that are not necessarily at 0 temperature. At the same time, I'm originally from mesoscopics, and where we were always interested in low temperature impurity problems. And with that, I would like to then jump in directly to the topic of today. So today I'm going to talk only about one work, okay? And specifically, a lot of credit goes to Jeff Mucky, who is a postdoc in the group now in Konstanz, and Lydia, who was a PhD student in my group still at ETH, who is now at Max Planck in Dresden, okay? And the idea is to look at ytterbium atoms and think about a multi-component setting where you could have one spin species that is controlled to be relatively kinetic, okay? And another spin species that you're going to confine to be like a single impurity pinned in space. And now, when this model is going to be there, we can think about the Fermi-Hubbard model for this type of fermionic species and the Fermi-Hubbard model for this type of fermionic species. And of course, here you will have a lattice kinetic energy as being very dominant, and here you're confined to have just a single atom that is pinned somewhere in space. And the interactions that you can do if you take this fully microscopic model, what you are going to see is that here we're going to get something that would look like a 1D quantum wire. And it's going to have now particle-particle interactions on the site of where this impurity is going to sit at. And there's going to be effectively 2 types of interactions that come about. One of them is going to be some sort of a Coulomb repulsion, where this impurity, because it's pinned, it's not a dynamic impurity like in the case of Hans-Christoph's talk, right? So it's going to be pinned here, and it's going to repel electrostatically particles from sitting under it, but it can also flip its spin. Okay, so it could start to flip-flop its spin, and then the question is the wire going to be cut off, chopped off? Is the wire at all going to interact with this impurity because of its own internal interactions, right? Or is it going to now mediate via spin flips transport through this wire? Okay, so this is the question that we're going to try to attack today. And for that, I would like to still remind some people about the Kondo effect. So how many of you know the Kondo effect? Okay, so I will still remind a little bit the Kondo effect. So the Kondo effect was already an observation that was seen in transport in materials in the 50s. Effectively, you take a metal and you start to cool down the temperature and you look at the resistivity. Now, as you're cooling down the temperature, you would expect that electron-phonon scattering will decrease. And because of that, you would expect that then conductance will increase and you will become more ballistic and less diffusive. At a certain point, however, what people saw in the experiment is that something new comes in and starts to increase logarithmically the resistivity of the material. And then it was understood over time that this is coming about due to the fact that there are magnetic impurities in the metal. And at low temperature, they could start to do exchange interaction coherently with the environment. They could start to do this with spins in the metal. And because of that, they will do that at lower and lower temperature. They could do that with more and more spins around themselves. And because of that, they will actually generate a screening cloud around these magnetic impurities. And then this screening cloud would already be married to the magnetic impurity and could not participate in transport. Okay? And this is then explain the increase over there. So this is then a cartoon of what I was telling you about. We could think of having something as the chemical potential of our metal, where we have sources of both spin downs and spin up. And the magnetic impurity could then have a co-tunneling effect that flips the spin without costing any energy. And this is then will be a coherent second-order perturbation theory source. And this is why it can only occur at very low temperatures. Okay? The effective Kondo model is then you have the metal, and then you have the scattering interaction, namely the spin moment of our magnetic impurity then scatters with a cross-section with flip-flopping states at the Fermi sea. Good. Questions until here? No. Good. From a many-body language of how these states then look like, then just to think about it, it becomes a many-body singlet. Namely, the magnetic moment has its ability to be either up or down. It will have exchange with its interaction, so it could flip-flop. And that means that actually the system now generates a many-body ground state that is a singlet, but it's a singlet with a whole screening cloud around itself, so you could really then think of writing it truly as a singlet where we had our magnetic impurity, where the whole cloud around, if the magnetic impurity is up, it managed to make the whole screening cloud around looking down, and so superposition as a singlet with it being down and the whole screening cloud pointing up. Yeah?
But in your case, the impurity has the same spin as any of the fermions, right? So should I think of this as you just cant down all of the spins in your cloud a little bit down and a little bit up? Because
okay, so the way it goes is that actually, so technically from a microscopic point of view, it picks up one of the candidates from the environment and it makes a full flip. Okay? And then it would have had a superposition of having the ability to do that with all of the others, right? And because of that, it starts to, and it's a resonant process. So it actually starts a cascade. Because now it flipped this, and now the impurity is, it's as if the impurity starts to delocalize. And how far it can delocalize actually depends on there is a way of calculating from the Kondo temperature, the length scale that you would need. And at 0 temperature, allegedly, it should proliferate through the whole system. That's kind of the idea. Okay?
But that effectively means that for any of the spins around it, on average, most of the time they're not flipped. So coherently speaking, they only flipped, canted down a little bit.
You're thinking Dickey, I think, right?
Bit,
so right in Dickey, then on average, the spin starts to look like this. Here, it opens up a many-body ground state that is gapped, where the many-body ground state looks like this.
Okay.
So then it's not, it's, yeah.
Okay.
Yeah. Okay, cool. Okay, that's the model again. So that was a little bit of introduction and context to the Kondo, and then technically this is a fundamentally interesting problem in condensed matter. In fact, most of the interacting materials that we're interested in condensed matter, one of the main methods of trying to attack them also numerically is using DMFT, and DMFT actually makes local environments that map to a Kondo impurity, and then you integrate out the Kondo impurity, and then you do that systematically to longer length scales. So the Kondo impurity is one of our most favorite Drosophila fly strongly interacting systems. And of course, if one can bring it to cold atoms, that would be great. Okay? And hence then the idea of the ytterbium gas and the setting that I now told you a second ago. So what did we do? Okay, so first of all, we're not the first people to propose looking at it. Okay, so the Kondo impurity, I told you, it already exists since the 50s in materials. I worked on it a lot in mesoscopic quantum dots. And then ideas of bringing it to ytterbium atoms were then explored by Gorshkov and Francesco Scazza. The microscopic Fermi-Hubbard model, you have it illustrated over here, where you could then use the fact that this impurity is inert and take at least the Coulomb interaction now between these two spin species into an effective new Fermi-Hubbard model, where you see that you have then kinetic energy only in this lowest rung, right? You will have the spin exchange that we said that will exist now between this species, and it's here local only under where it could exist. And the repulsion will appear as an effective barrier here that is imposed by the fact that there is now a spin parked over here, and on top of it, you're going to have Hubbard interaction in this chain. Okay? So we could, what is important for us to notice is that also, like we heard in the previous talk, we could first deal with the Fermi-Hubbard chain, namely the black part here of the Hamiltonian, and then we could think about what happens to our quantum wire in the presence of this additional impurity, okay, where we're going to have contributions both from these magnetic terms and from this repulsion term by the fact that this presence of another fermion here repels the others. And so let's start with just the wire. The wire, I actually don't overly need to say it in this community, but the wire, effectively, if it's not interacting, we're going to be able to write any fermion with a cosine, right? If we just have tight binding, we'll have a cosine dispersion, but at low temperature, not low temperature, at the continuum limit, we're just going to have right movers and left movers at whatever the chemical potential is going to be. And then because of that, we can think about it that many-body interactions leads to very big impact. You can actually not perturbatively treat quartic collisions on a wire. And this is exactly, so my slides flipped order. I have okay. So this should have been the non-interacting, and then we saw a collision, and then now we would probably see, there should have been another collision. Okay, anyway, whatever. So the thing is that collisions in a wire are actually fundamentally impacting the dynamics of the system, so it's very tough for us to think about taking out a particle and scattering now to new particles with new directions. It's the same way that the fact that if I want to go from here to the exit door, I can just move around. I will just be a little bit slower, and this is why I gain an effective mass. But if I stand in the queue to the supermarket, I cannot pass the person in front of me. Okay, so it turns out that if instead of thinking about the underlying fermionic particles over here, you would then move to particle Hall excitations relative to the chemical potential of the system, you can bosonize the system, and then effectively the 1D interactions in the Fermi-Hubbard around such a chemical potential would look and map onto the Lieb-Liniger as well, right? So they are cross-talking to each other. And the bosonization procedure, Haldane already proposed it in the 80s. You're keeping a notion of the fact that you're a fermion by something called the Klein factor, and then you're just saying that the rest of what annihilating a fermion at some position x will do will actually end up doing some sort of charge ripples and spin ripples in the wire, right? Because someone takes someone else from the queue in the supermarket, everybody will start to shift around. And now these bosonic fields, which are related then to the density and the currents in our wire, have then bosonic commutations. And what is extremely cool is that then you could take this interacting Fermi-Hubbard model, and you can actually write it as a quadratic action or Hamiltonian for our bosonic fields, okay? Where it's then characterized by these so-called Lottinger parameters, and these Lottinger parameters are then showing how the density and spin waves are now split into having different effective velocities in this wire, okay? And then you could see how these parameters are related to the interactions. Good. So that was what we would want to do now for this wire over here. And it's going to manifest itself now in two types of studies that we are doing then further in order to understand then what the impurity is doing over here. Where I want to remind you, we are trying to understand again this Quasimodo paradigm, right? So we brought more components, and now each of them can have its own interactions, and we need to figure out are the systems making something new that is more interesting? Are they breaking apart, right? So this is the philosophy. So in the language of Lottinger liquids, so we could take that Fermi-Hubbard Hamiltonian plus impurity, and we can bosonize it. When we bosonize it, we see that we diagonalize. We had the previous Hamiltonian over here. This is already solved the black parts of, okay, whatever. It solves already the black parts here, but now we need to also write explicitly these parts in this bosonized field language, and they end up giving us a whole bunch of magnetic sourced contributions that look like sine Gordon terms, okay? And they're going to give us additional potential type contributions here. And all of these contributions are now entering, and all of these contributions may be relevant, or may be marginal, or may be irrelevant. And in order to figure out what they do, we are going through the process of renormalization group analysis. I will not explain it due to time considerations, but effectively you're integrating out high energy levels in order to see where the energy would flow when you go to lower temperatures. And we are effectively looking at these beta functions, namely how the coefficients of these 7 Hamiltonian terms that we find are existing, how they flow as we go to lower and lower temperatures, okay? And because we go to lower and lower temperatures, it pertains to lower and lower energies, which means larger and larger length scales. So this is why usually then you think about going to the thermodynamic limit with this at 0 temperature to figuring out what's going to happen. So you see it's a huge mess. Everything flows, and everything flows in a coupled fashion. And we do that every time for a different type of originally interacting wire. Okay, so we assume there was a wire, we put an impurity, and we let it flow. And when you're doing that, you could start with different initial parameters for our Lottinger liquids, and then see how these beta functions are flowing. And we had different types of flows. We allowed sometimes some of the flows to actually be pinned, and then flow only subparts of them, and sometimes we allowed all of them to flow. Okay, this is how you systematically then analyze it. And then what you see is how these then prefactors grow, and if they grow, it means that this contribution becomes more and more relevant. So for example, if we had a contribution there that wanted to split the wire into two, and it becomes the most dominant term, it tells you that at lower temperatures, this wire should now be cut in two by this presence of the impurity, and the system should become insulating. And then what we do is we are looking at which one of these prefactors crosses one first. This is where then the perturbative RG treatment is no longer valid. And we are saying then the system will most likely fall into that order. Okay, this is the treatment that we're doing. And we're collecting this. And we are collecting this by allowing different types of subparts of these beta functions to flow. And we're also comparing it to different known analytical limits. So there are some analytical limits that are kind of like poor man's scaling limits and fitted symmetry point limits that, again, I don't have time to get into just now. And we are able to, by that, actually reproduce when are you going to get Kondo manifesting in the system. Namely, the impurity now manages to open a gap, but that leaks through the whole wire as well. And when it doesn't manage to do that, it actually decouples, the impurity then decouples from the wire. And the traditional historical results actually came all the way up to here, where you could see that actually here there would be, red parts would be that you have Kondo, yellow parts tells you that you will just have a weak scattering from the impurity and there will be no Kondo. And actually now, when you add more and more of these beta functions into the story, what we could find out is that this potential scattering eats up more and more regions of the Kondo, okay? And makes it that the repulsion by the impurity here actually makes Coulomb blockade around itself. And by that screens away the ability to do magnetic flipping and suppresses the ability to do Kondo. Okay, so this is what you actually see from this study. But at the same time, we still identify that there will be regimes where you should still be able to have magnetic correlations manifest. It depends on the interaction in the Lottinger liquid as well. Okay, so that's what we see. We are also able to then see how the Kondo temperature then changes as a function of this potential relative to the exchange, the potential blockade relative to the exchange. And also here what we see is that the higher the potential is, the lower the Kondo temperature becomes, which means that it becomes harder and harder to generate these magnetic correlations in the wire via the impurity. Okay, good. So I still have some time. Okay, I still have 2 minutes, right? 3 minutes. So you tell me, hey, it comes with this Wilsonian RG and in some zero temperature. Can I trust this at all? So we agree with you. And what we did was to say, okay, we need something else to use to check this whole construction. And then we used matrix product state representation of the system, and we did the MRG on it. Okay. So specifically, but we wanted at the same time to have the ability to cross-relate to these works. So we were trying to target how do we get exactly these Lottinger liquid parameters, and we managed to actually, via our DMRG process, to identify different starting points that pertain to these markers on the plot. Okay? So we are doing that. So the first thing we do is the same thing as we did in the RG. We first eliminate the impurity. We do DMRG on the Fermi-Hubbard. And we are looking at the compressibilities of the many-body ground state that we find via DMRG. And by this, we are extracting the effective Lottinger parameters that are in that wire. And you see that then we could change the filling, and we could change the Hubbard U. And we could then get different values of K. So by doing that, we could target the DMRG many-body ground state of choice, the parameterization of choice, and say, okay, that would then be that K sigma and that K rho that we are interested in. And now we add the impurity. And what is nice that we also learned to do from the quantum dot era is that when you do this MPS DMRG, you get the many-body ground state, but you have it in MPS form. So you can also go and look at standard observables, like what can be then measured in experiment, like compressibility. Or we can also look at the singular values of our MPS decomposition and understand something about, for example, entanglement in the system. Okay? And in our context of having the question of, do I form a singlet with the environment or do I not form a singlet with the environment? This is extremely useful because we could go to the position of where our impurity is, chop it off from the Fermi-Hubbard wire, and then ask, was it in a singlet? And we can ask whether it was in a singlet. I'm finishing. Okay. Whether it by looking at the purity of the system or at the entanglement spectrum of the system. If it's a singlet, it will be 1/2 for the purity. So we go and we do that, and then we park ourselves at these locations, and then we are changing the microscopic parameters of how you couple to the impurity. And indeed, we find that there are some regimes, critical regimes, where you could have Kondo, and critical regimes where you cannot, and you could see that out of this entanglement entropy or from the purity of the system. I will finish because I should finish. With all of this, we could do a whole bunch of new questions that come out of this. This is also then interesting for the condensed matter people in the sense that it proposes new types of protocols on how to study Kondo. Because in condensed matter, we study Kondo only via transport. And here, if you have the impurity in your hand, you could do some Landau's in there and do tomography on it, and then figuring out other observables for Kondo. So with that, I would like to thank you for your attention.